Okay. One of the next remark is I've added a due date to another batch of problems on the first assignment. It's on the web page. You can look it up. I won't go into that now. This is a draft of the contents. Now, it's not serious. I don't think there's any chance that I'll get to part 4. I may not finish part 3, but anyway, that gives me a goal. So I decided I want to start by talking about state transfer on cube-like graphs. I could have done this earlier and probably should have, but it's still interesting. I'll do it now. So I remind you the cube-like graph is just a k-graph for z2 to the d. So the vertices are the binary vectors of length d, and 2 of them are adjacent if they differ in exactly 1 position. Okay, so so that's a cube-like graph. Now if you choose the connection set, okay, so 2 elements are adjacent if their sum or the difference lies in the connection set. If you choose your connection set to be the standard basis, then the graph you get is a d cube. Okay, so that's an easy exercise. It doesn't seem strange. So you get the d cube. So the d cube is a cube-like graph, so the name is reasonable. Now, I'm going to be viewing Z2 to D as a vector space. I've never understood why introductory courses in linear algebra don't go over do some stuff over Z2 to D. I mean, it's important, it's useful, it's got applications, and it's easier. But there it is. And so I want to, in a sense, I've told you if I choose my connection set, then I get a k-graph for Z2 to D that's cube-like. Now I'm giving you another description in terms of matrices. So the idea is if I pick a binary vector W, and I'm going to define a linear map from Z2 to D to itself. It's a vector space, so it's just a plain old-fashioned linear map. And the rule is that it maps U to U plus W. So it just adds W to each vector. Now, if you add W to U plus W, you get U back again. So you see that the square of a W is the identity. And in fact, it's a permutation on the vertices, or on the vertices of the graph, and the orbits of this permutation all have lengths too. It swaps things in pairs. Okay, so I'll come back in a minute. The other thing is that if it's 2 different vectors, well, actually, it doesn't matter the different or not. 2 vectors V and W. Well, actually, I've got okay, that's right. Any 2 of these matrices commute, and the point is that AU times AV is equal to A U plus V. Now that's almost worth going off and doing a little calculation, but so that because U plus V is equal to V plus U, we get that these 2 things commute. So we have a collection of matrices. Okay, now we have one of these matrices for each element of Z2 to the D. Okay, we're not going to be using all those, but we have one for each. Any questions to this point? So as a matrix, if you arrange things in the right order, you can assume that AW's got a sort of block structure 0, 1, 1, 0 and copies that all the way down. So, but in general, since it's a symmetric matrix, and its trace is 0 because it doesn't fix any vertex. So it's a symmetric matrix 0, 1s with trace 0. So it's the adjacency matrices of a graph. Now, it's not the world's most interesting graph. It's just the consists of 2 to the D minus 1 vertex just doing copies of K2. So it's a perfect matching or a 1 factor. Okay, and so we have to. So my point now is I've defined these operators AW, and what's the relation to what we're doing? I claim, and is that the adjacency matrix of my cube-like graph is just the sum of the matrices A sub W for W in the connection set. Now I can probably leave it on the exercises. It's not too difficult. The trick is when you're constructing Cayley graphs is to think of the elements of the connection set as being colored. And so in general, each arc is going to have a color. And if you're dealing with a cube-like graph, the arc and its reverse the same thing. So each edge has a color. And so if I pick out the edges color blue, I get a disjoint copies of K2. So this is a natural. It's not particularly difficult. The other thing, which I think I did prove, is that if X is cube-like, its eigenvalues are integers. Now, there's an assignment question on this, which basically constructs an eigenvector, and then you can, from this you deduce and you see that the eigenvalue is integer, and then you see you've got the eigenvectors you've got form an orthogonal basis. So you deduce that the eigenvalues are integers. Okay, so that's the proof in the assignments. Another approach which is worth going through, I think, is that the eigenvalues of AW plus or minus 1, because the minimal polynomial of W divides t squared minus 1. In fact, it will be t squared minus 1. Okay, and because the trace is 0, 1 and minus 1 occur with equal multiplicity, which I don't really need, but why not? Now, the next comment is that the matrices AW are symmetric and commute, and that should be a so. Let me be picky and fix this. So, oops, got mad here. Yeah. So ZD has a basis of eigenvectors, each of which is there's a basis. It has a basis of eigenvectors, and each of these eigenvectors for Z to the D is also an eigenvector for each of the matrices AW. Okay, and so now you just say, well, if you apply AX to Z, that's the same as applying the sum of the AWs to Z, and so you get a sum of this form. That's a badly drawn Z there, and the point is that this coefficient here is an integer, okay, because it's just an eigenvalue of one of the AWs. Okay, so the eigenvalues of a cube-like graph are integers, and so you've got two proofs now. You've got the one in the notes, which is actually giving you the eigenvectors as well, and a proof here using the fact that if you've got commuting normal matrices, then you can simultaneously diagonalize them. Okay. And that's something which will keep coming back. Now, if the eigenvalues of a graph are integers, then there's an integer m such that if I take the transition matrix for the continuous walk, then u of m pi is equal to identity. And the point is that if u of t has got this spectral decomposition, and you put in t equals m pi, then you've just got to choose m so that m theta r is even. Okay, so you choose the smallest integer m you like such that m theta r is even, and then that value at time m pi, u of at time m pi, u is equal to identity. And that means the quantum walk is periodic with period m pi, or perhaps dividing m pi, but it's not fast. So it just keeps returning in all lengths pi. So it's periodic. Okay, and so it's enough for if the eigenvalues are integers, the graph itself is periodic. Now, this is closely related to the questions about periodic vertices and walks, but we don't need to think about that right this minute. And so I won't go into anything more about it. We'll say the graph is periodic if there's a time tau such that u of tau is equal to gamma times I for some gamma. Now, this looks a bit more general than that, but we'll see, in fact, it's not really. The point about the gamma, though, is u of t is a unitary matrix. So this is a unitary matrix. Now, I is unitary, and gamma times I is unitary if and only if gamma has got norm 1, complex number of norm 1. So gamma must be a complex number of norm 1. Okay. Now, if you're working, this comes up whenever you work explicitly with u of t, you'll end up getting these things. They're often called phase factors. If you work with the density matrices, you don't see the phase factors, which is one of the advantages. And I've got a few remarks about it. The first thing is that, well, but it's just saying what I just said, that gamma here must have 31. Secondly, the determinant of the right-hand side is gamma to the n. The determinant of the left-hand side, by one of your exercises, we had the exponent to the trace as the determinant of the x. So we get the determinant of the x is equal to the well, here it is, the determinant of the x. It's x with the trace. Now, A has got trace 0, so you're looking at 1. And so gamma is an nth root of unity. Now, n's a bad letter to use there. It should be, let's actually fix it. Some people will see this. So it's an nth root of unity. And so if ut is equal to gamma times I at some time, then there's it's a longer time which u of t is equal to identity. So this, oops, this statement is not really more general than this. Okay, so U of t is a scalar times the identity, or U of t is equal to identity. It makes no difference when you're trying to calculate what's happening. The other comment is that the path on 3 vertices is periodic, but its eigenvalues are not integers. So it's not true that the graph is periodic if and if its eigenvalues are integers. Something very close to that is true, but it takes more effort than you would expect. Now, it's clear that if I have the eigenvalues of the graph of the form √3 times integers, then the graph will be periodic. The problem is to show that if the graph is periodic, the eigenvalues are of that form. And we'll be coming back to that. So now I want to get back to my cube-like graphs and perfect state transfer. And there's a very simple condition. So we've got our connection set, which is a subset of the elements of Z2 to the D. We might as well assume that a subset of non-zero elements of Z2 to the D. And I do need for this. And I'm defining lowercase c to be the sum of the elements of the connection set. Okay, so that's where, each element of the connection set is a binary vector of length d, and so we just add them up. And if the sum is not 0, then X emits perfect state transfer from V to V plus C for all V in Z2 to D. So this gives us lots of examples of perfect state transfer. And the other thing is, if you discover that the sum of U's over your connection set is 0, well, you're free to add one. Well, just delete one element from the connection set. The sum is no longer 0. The sum is now equal to the element you deleted. Or you can add one more element, and the sum is now the element you deleted. So this gives you lots and lots of examples of perfect state transfer. It's probably the most general construction we know. In terms of producing a big family all at once, it's a little bit arbitrary because we have plenty of constructions for infinite families, and one infinite family is as big as another, but let's leave that alone. So, okay, so the question is to prove this. Okay, now we're starting. I've got my adjacency matrix as a sum of these operators A sub W, and so I've broken up into a number of steps. I've gone from A to C, not the fun. Now, the first thing I just want to notice is that if, when I gave my first example, perfect state transfer, I looked at K2, which is a cube-like graph. Okay, and I wrote down the adjacency matrix 0, 1, 1, 0, and I noted that A squared is equal to identity, and then the power series expansion is easy. Now, I don't need anything too special. If B squared is the identity, then the X of ITB can be written with this. So this is a generalization of Demar's law. Okay, you just prove it by expanding the series. Okay, so there are two terms. There's a cosine term and the I-psi term, and you just use the series expansion. Now I've gone straight to C here. That's fun. There's probably no D either, but let's not worry. So now the claim, and I probably didn't say it. I didn't write it here. I should say there's perfect state transfer at time pi on 2. So there's a few gaps. Well, we'll come back to that. There's nothing serious, but questions to come up. So if I choose t to be pi on 2, then cosine pi on 2 is 0. And the x of AW, x of A is just a product of the x of AWs. And so it's just a product of the things that form I sine pi on 2 times AW. And so you deduce that the I'm not doing very well here today. That would be better. So at time pi on 2, the transition matrix is equal to I to the power size of the connection set times A sub C, where C is the sum of the elements. Okay, and so from that we see that if the sum of the elements is 0, then in fact U is periodic at time pi on 2. Because the eigenvalues are integers, U would always be periodic at time pi. Maybe 2 pi. Anyway, so this factor of I doesn't play much of a role, and so then what follows here is the proof of that claim. So we're saying AW can be written as sum like this, and we just say the x for the sum is product of the x's, and then we just use the Demar's theorem, and so we get this. Okay, So we get this. So we get, that tells us we get PST from any vertex u to u plus c at time pi and 2 if the connection set sums to something that's not 0. Okay. Now, now you can show that if you do get PST on a cube-like graph, the time which occurs will be 2 pi over power of 2. And so the question is, at what other times can it happen? Chong and I have a paper where we worked out what happens for time pi and 4. It turns out you can associate a binary code to each cube-like graph, and we can give a characterization of the cube-like graphs with PST at time pi and 4 in terms of the property of this code. Okay, now we did that, and I thought a bit about pi and 8 and decided it was too hard, and I sort of crossed my fingers and I hope maybe you couldn't do it faster than pi and 4. We had them all. But then Ada made a nuisance of herself and proved that you could have produced an infinite family of examples where the time to PST was, you can make it as small as you wanted, modulo being pi over a power of 2. And so we don't have a characterization of what goes on beyond pi and 4, not even for pi and 8. I still think it might be, it's not clear. I don't expect, well, I'm not confident that there's a nice, easy description of what goes on at these higher values. But I don't know, and there's an open problem hiding there. Any questions again? I have a paper on this with Severini and Anna Bernasconi, and they wrote down their own proof of this and makes it more complicated. But anyway, this is the a very simple proof of the useful fact. Now, since I'm talking about cube-like graphs, it's natural to think a bit about vertex transitive graphs, and I might come back to this more later on, but I just want to make a few remarks at this point. So we established that cube-like graphs have PST at time pi and 2 if the connection set sums to something non-zero. I just want to think a bit about vertex transitive graphs. I mean, it's not an unreasonable goal to say, can we at least decide when vertex transitive graphs admit vertex A transfer? Or if you're less ambitious, you might say, do Cayley graphs admit vertex A transfer? So these are questions you could ask. One problem is that you need information about the spectrum of the graph. And it's an illusion that we can compute the eigenvalues of a Cayley graph in any rational way. Okay. And so, for example, the people proved that the Ramanujan graphs, and so that they were had a construction of Ramanujan graphs. And basically, the difficulty reduced to computing the eigenvalues of a Cayley graph for a two-dimensional linear group. So it wasn't even a particularly nasty group. It was a bog standard group sort of thing you'd think about if you wanted to work with some group that's not just a symmetric group. Okay, and they had to compute the eigenvalues, and for that they needed deep theorems from number theory. So getting the eigenvalues of the Cayley graph is in general not easy. It's different if the Cayley graph is abelian, and there are some other special cases. But so in general, getting the eigenvalues of the Cayley graph is not particularly easy. So I don't necessarily see that doing Cayley graphs would be any easier than doing vertex transitive graphs. Now there is a restriction about PST on vertex transitive graphs, and that's what I want to discuss. So I'm going to assume that X is a vertex transitive on n vertices, and that it emits perfect state transfer from vertex 1 to vertex 2 at time tau. Okay, so writing this out gives me this equation. Now the left-hand side is an outer product of U tau applied to E1, and this is the outer product of E2. So it follows from this that U tau applied to E1 is a complex scalar times E2. This is our phase vector coming back again. And as before, since U of t is unitary, this is going to have norm 1, although you need this. I can't argue that it's an eigenvalue in this case, but anyway, so it's going to be complex norm 1. Now, I have this equation, and what I propose to do is just take the complex conjugate of each side. Now, E1 is real and E2 is real, so I just get that UT bar is equal times E1 is equal to the gamma bar applied to E2. Now, the complex conjugate of U of tau is U of minus t because our Hamiltonian is symmetric. And so this is U of minus t and this is gamma inverse. And so I can swap things over and I get that U of tau E2 is equal to gamma E1. So this is another proof that if I have perfect state transfer from 1 to 2 at time tau, then I'll also get perfect state transfer from 2 to 1 at time tau. And it says a little more. It says that the phase factor, if you write it down, is the same in both cases. But we don't need that. So we have this. So U of tau is, well, I'll leave it at that for a minute. Now, if P is not a morphism of X, now I'm thinking of P as a permutation matrix. Now, well, it commutes with A. That's the definition for a permutation matrix to be an automorphism. Now, U of T is a polynomial in A because it's a linear combination of the Schur idempotent of the matrix idempotent of A and the matrix idempotent of A are polynomials in A. Okay, so if P commutes with A, it commutes with U of T. And so then you check and then you get this, that U of T applied to P, image of E1 under P is equal to gamma times image of P2. So U of T is swapping things in pairs, but there's this phase factor there to confuse things a bit. What you get is you can assume that U of tau has got this form, gamma times direct sum of 2 by 2 blocks. Okay, so this is the same structure as our perfect matchings from when we're looking at the cuboid graphs. Not that's directly relevant. So U of T has got this form, and so then, and so in particular, gamma inverse times UT is in the automorphism group of X. So this is telling you, okay, perfect state transfer on a vertex transitive graph, you can divide the vertices into pairs, and each pair you get perfect state transfer from one vertex to the other. So if you get perfect state transfer on a vertex transitive graph, you get a lot of it at once. The other thing is that since this is in the automorphism group of X, it's an automorphism, but any automorphism of X commutes with the adjacency matrix, and this is a polynomial in the adjacency matrix, so any automorphism of X commutes with U of tau. And more generally, it commutes with this matrix. So this is an automorphism graph, and it commutes with every automorphism, so it lies in the center of the automorphism group. So it's in the automorphism group. In fact, it's in the center of the automorphism group. And one consequence, for example, is that there's no perfect state transfer on the Peterson graph, because we saw that the automorphism group of the Peterson graph is the symmetric group on 5 letters, and its center is trivial. So this gives one proof that the Peterson graph does not emit perfect state transfer. We'll see more as we go on. But so we can't, and so in particular, if a vertex another simple consequence is if the vertex transit graph emits perfect state transfer, the number of vertices is even. So, okay. So I talked about PSD on cuboid graphs and vertex transit graphs, and now I'm going to get back to the main theme. So what I'm working towards is a proof of the fact that if you there's only finitely many connector graphs with maximum valency K which contain a periodic vertex. So this is saying, you can view this as saying that PSD is rare. Okay, now there's a reasonable amount of tuning going into the proof. I need concrete information. I'll be spending a lot of time looking at the eigenvalue support for vertex states. Okay, that's where the machine is coming from. And I would need both linear algebra results on the eigenvalue support, and I'll also need some number theory results. And so in my next lecture, I'm going to be reviewing a reasonable amount of number theory. But so we'll come back to that. So also there is the number theory that I'll be discussing. There's a version of it in the notes, the course notes, or the text that Gabriel and I put together. So there's something there. But anyway, I wanted to talk about the eigenvalue support. Now, and it turns out that for that, I'm going to need to use a version of the Perrin-Frobenius theorems. Now, the Perrin-Frobenius, well, usually there's about 3 parts to it. And when someone says this is a proof of the Perrin-Frobenius theorem, it's not always sure how many of those parts they're bothered to prove. But I won't go into that. But they provide important information about the largest eigenvalue of a non-negative square real matrix. Now, it has to be non-negative, has to be square, it has to be real. It doesn't have to be symmetric. But doing the general case, it's easier to do the case where the matrix is symmetric, and that's the only case that I need. So I'm going to prove version of the Perrin-Frobenius theorem, or some parts of Perrin-Frobenius theorem, in the situation where the matrix is symmetric, so the adjacency matrix of a weighted graph. I don't care about weights. Okay. The other point I'll make, the history of this is a bit complicated. Perrin proved these results under the assumption that all entries of the matrix were positive. And then Sabrina later pointed out to me, he remarked that it was easy to extend this to the case where some power of the matrix was positive. Frobenius wrote down the details, and so now it's called the Perrin-Frobenius theorem. But it's, in some sense, it's all due to Perrin, apparently. So I want to prove the Perrin-Frobenius theorem. Now, I've got a couple of reasons for doing it. One is because I want to, the result that I need is that if the graph's connected, there's a unique largest eigenvalue, and the corresponding eigenvector has all its entries of the same sign and none zero. So I'll say that the eigenvector has all entries positive. Now, that's a lie, because if you've got an eigenvector z with all entries positive, then minus z is also an eigenvector and all its entries are negative. So when I say the eigenvector has all its entries positive, I'm going to say they all have the same sign and number zero, but I'm just going to abbreviate by saying it's positive. So just be a little careful. Okay, the other reason I'm doing this is because, well, something about to prove, but I guess I'll bring a bit more machinery. So I'm going to be working with what is called the Rayleigh quotient of the matrix. So it's a function, you've got a matrix acting on a vector space, and so it's a function on the vector space that sends the vector x to x transpose x over x transpose x. The assumption is x is not zero. And so this is called the Rayleigh quotient of M. And just as a side remark, if x is an eigenvector for M, then the Rayleigh quotient of x is just the eigenvalue. So that will appear without mention shortly. So now this is the theorem I want to prove. So I've got a symmetric real matrix. Okay, and the first claim is that the maximum value of the Rayleigh quotient is realized by an eigenvector z of M. So we can write max rather than sup and leave the analysis out of it. Further, if M is non-negative, then the vector is non-negative. And if the underlying graph is connected, then all entries of Z are positive, modulo what I just said. And the eigenvalue belonging to Z is simple. So this is quite a bit of information. The Perrin-Frobenius theorem plays an important role, for example, in the study of Markov chains, because you're looking at powers of non-negative matrices, and they aren't necessarily symmetric. Okay, but for what we're doing, see, what I want to do is let me do this in color. If I have a vector z, the eigenvalue support of z is going to be the set theta r, such that the rz is not zero. Okay. And so, okay, so I want to work out what the eigenvalue support is. Now, this vector z, if we're looking at vertex states, it's just going to be a standard basis vector. And so we see that if the largest eigenvector is positive, then it lies in the eigenvalue support. And so the conclusion will be that the eigenvalue support always contains the largest eigenvalue when the graph is connected. And since we have no information about the eigenvalue support at this point, that's progress. Okay, and it plays a role at various points. So we're going to use this to, one use of this is to show that the eigenvalue support is not empty in interesting cases. If you start with the empty graph, then the situation is different, but that's on you. So I want now there's two. So I've broken up the proof into some number of parts, 4 probably. The first thing is that the maximum. I did show that the maximum exists. Okay. Well, the point is that the Rayleigh quotient is a not continuous function on the unit sphere. Is a continuous function on the unit sphere, and the unit sphere is compact, and so by a theorem from analysis, it realizes its maximum. Okay, so so it has a maximum. Okay, now the next step I want to do is to prove that that maximum is an eigenvector of M. Now, notice the thing here is what I'm proving is that symmetric matrices, symmetric real matrices, have eigenvectors. as a consequence of this. Okay, and I haven't used the fundamental theorem of algebra, which isn't a theorem of algebra and probably isn't fundamental. But so the point is we're constructing an eigenvector, okay, without using the characteristic polynomial or anything. And in some ways, this is closer to the way you actually use eigenvectors and things in practice. I mean, nobody computes eigenvalues, even the 3x3 matrices. It's not clear you waste time putting a characteristic polynomial. And so the minute people have calculators that are powered by electricity, they found other ways of computing eigenvalues. Okay, and so, but the point about this is we're going to prove this. It's a reasonably simple proof, and I'm pointing out that it is giving us the existence of eigenvectors, and we're not using the fundamental theorem of algebra. Okay, so we're going to assume that we've got a unit vector Z which maximizes the Rayleigh quotient. Now, what I want to argue, well, that means if I replace Z by some vector very close to it, the Rayleigh quotient can't go up. It can't increase because Z's the maximum. Okay, so how am I going to do that? Well, I'm going to take a small vector H, so you can think of having it as order epsilon, and I'm going to assume that H is orthogonal to Z. I mean, it doesn't make sense to replace Z by 1.2 times Z. Okay, you're trying to stay on the unit sphere. So small vector orthogonal to Z, and so here's a quick computation. The squared length of Z plus H is Z comma Z plus 2 copies of H comma Z plus H comma H. Now H comma Z is 0, and H comma H is order epsilon squared. And so ignoring the terms of order greater than 1, we get that the Z plus H is a unit vector. Now, this looks like a sloppy analysis proof, and I got 2 responses to that. The first is it's fairly easy to turn this proof into something that would make your analysis instructor happy. The second thing is I could talk about using the infinitesimal calculus, and there are books on that. And so it's perfectly rigorous, and it's more conceptual than the putting in all the epsilons and deltas. So if you want to fill this out and add the details, fine. But so my point now is that Z plus H. So what I'm going to say is that if Z maximizes Rm, then the Rm evaluated at Z plus H cannot be bigger than Rm evaluated at Z. So that's my consequence of that. Now, and so let's do that. Well, we want to get the eigenvector first. So we now compute Rm Z plus H using the same approximations as before. And so in this case, we get these 2 terms, which are equal because one to the transpose of the other. And we get a term of order E squared. And so you've got Z transpose MZ plus twice this. Now, if Z maximizes Rm, this must be 0. If it's negative, I can replace H by minus H, and then I'll get it. This will be this will be positive. So if this is non-zero, Z wasn't maximal. Okay, so we've concluded that if Z maximizes Rm, then H transpose MZ is 0. Okay, now I wonder, sort of encode this in terms of subspaces. So our statement then, what we've shown is if H transpose Z is equal to 0, then this is equal to 0. Or equivalently, H is in the orthogonal complement to Z if only it implies that H is in the orthogonal complement to MZ. So that says that the orthogonal complement to Z is contained in the orthogonal complement to MZ. And now I take orthogonal complement to both sides, and I get that the space spanned by Z contains MZ. And that's the definition of an eigenvector. Any questions? Okay, so we've proved that the Rayleigh quotient is maximized on an eigenvector. And so now we just have to deal with non-negativity. So the first thing I said that if M is non-negative, then I can assume that the entries of Z are non-negative. And this is more combinatorial than anything. If first a notation, I'm just going to use absolute value of n and note the matrix you get by taking the absolute value of each entry. And then I noticed that since m is non-negative, the absolute value of x transpose mx is by some form of the triangle I call equal to that. And since m is itself non-negative, we get this. So, but this is a Rayleigh quotient. And if x is a unit vector, so is the absolute value of x. And so we can assume that if we find a vector which maximizes x, we can arrange for its entries to be non-negative, just replace them by the absolute value, and we'll add something. In fact, the vector you first found will have non-negative entries, but that's the point would be that we get that. Okay, so good. So this tells me that if m is non-negative, then the eigenvector belonging to the maximum, or belonging to the eigenvalue, no, the eigenvector belonging to, that maximizes the Rayleigh quotient is non-negative. And probably at this point, we also get that the eigenvector is non-negative, since mz is equal to lambda z, and m's non-negative and z's non-negative, so lambda must be non-negative. Now the next step is simply that if the graph underlying m, so m is a symmetric matrix, but the entries are real, not necessarily zeros and ones. And the claim is that if the graph is connected, then the entries of z can be assumed to be positive. And this is now, this is going back to the idea that if I have a function on the vertices of a graph, then so I have a function f and it gets mapped to AF, then the value of AF on U is just the sum of the value of F on the neighbors of U. Okay, now I'm writing this out in more detail here. So if MZ is equal to lambda Z, then lambda Z, the kth entry of lambda Z is equal to this sum. Okay, so that's just, okay, that's just standard algebra. Now, if Z is positive, that probably should be a ZK. Okay, I can fix that. And some entry, one of these entries, MKL, is positive. Then, so if one of these entries, MKL, is positive, so that's no, I think if it's not the ZK, is it? What am I doing? Yeah. And okay. Now, lambda times k is the, or an eigenvector is a function, and lambda times k is the sum of these things. Now, yeah, so the point is if zk is positive, then at least one term in the sum on the right must be positive. So if zk is positive, it's got a positive neighbor. And now induct. That's where you use the fact the graph's connected. Okay. Okay. So that's a proof of pair and Frobenius for the case that the matrix is symmetric. There's a bit more. It's if you want to do the general case, the problem in a certain sense is the existence of the eigenvector to show that there's an eigenvector which maximizes it. And so you need a strong, I use the fact here that the if you're maximizing a continuous function, a compact set, then the maximum is achieved. To do the general form of the pair and Frobenius, you need some, well, the easiest way to do it is to use some fixed point theorem from topology. And you say that if I've got a non-negative matrix, it maps non-negative vectors to itself, and then you wave your hands and say this implies that it fixes some non-negative vector. So there's some extra work at that point. The other details are much the same as what I've just done. Now, the pair and Frobenius theorem, fully stated, also tells you that if you have an eigenvalue, the same absolute value as the largest eigenvalue, then the ratio is a root of unity, and the graph has got some regular structure, but we won't go into that. We don't need it. Okay, but the other point is that I haven't done is that the maximizer, the eigenvalue corresponding to the maximizer is simple. And I think I'm going to leave you to read that. Let's do it. So if we assume it as before that Z maximizes the Rayleigh quotient and that it's an eigenvector with eigenvalue lambda. And so now suppose that lambda is not simple. Then there's an eigenvector y with eigenvalue lambda for M. And you can assume without loss that it's orthogonal to Z. Okay, you can find a linear combination. If y is not, you can find a linear combination of y and Z, which is. And so some entry of y must be negative because the entries of Z are not positive. And so now I've got this eigenvector y with some positive entries and some negative entries, and I've got my eigenvector Z. What I claim is I can find a constant C such that x plus cy is non-negative and has zero entry. And now I go back to the proof in the previous part and argue that can't happen because the neighbors that vertex will have non-negative weights, and so that's so you're using the machinery there. These details are also in my book with Royal, for example, and there's also a proof of Parafrobenius in the notes. Although I think this might be a little simpler than our first version. Now I'm going for time. Pretty good. This is terminology you may well be familiar with. So the spectral radius of a square matrix is the maximum absolute value of an eigenvalue. If you're dealing with operators in infinite dimensions, it's a little more complicated. And so for a symmetric real matrix, this is just the largest eigenvalue. And unfortunately for you guys, I'm usually going to denote it by rho. And so there's a danger from time to time that rho will turn into an E, but I'll try and get it right. For a connector graph, rho is simple, as we just saw, and we can assume the associated eigenvalue is positive, and that vector is often referred to as the parent vector. Okay, so that's the basic facts for, so, okay, I can go on a little bit further. So I want to talk about the size of the eigenvalue support. Now this, as I said earlier, the size of the eigenvalue support of the pure state is just a set of eigenvalues theta r such that E sub A is not zero. Okay, if your state's not pure, there's a more complicated definition, but it reduces to this. Now the eigenvalue support clearly always contains rho because its entries are non-zero, and so the A entry of the parent vector is not zero. So the size is at least one. Okay. Now my comment now is it can't be exactly one. Because suppose that it was, now we can write the sum of the idempotencies is equal to the identity. And so this statement is certainly correct. But the only terms in the sum that matter are the ones where EA is not zero. And if we're assuming the eigenvalue support's got size 1, we're saying that EA is equal to ER applied to EA. So that says that the A column of that ER is just a standard basis vector. Now, if that's the and so from this, we're forced to conclude, and this vector must be the parent vector. Now, if your parent vector has only got one non-zero entry, and all those entries have to be positive, that means your graph's got exactly one vertex. So the only way you can get the eigenvalue support to have size 1 is to start with the graph on one vertex, and there aren't any interesting questions about quantum walks on that graph, so we'll leave it. Okay. So that tells us too. Now, I won't go into it now. So this gives us a lower bound. And the point is, if you know nothing about the eigenvalue support, then even partial results like this can be useful. They give you some leverage and get you started. So we can assume in general that the eigenvalue support contains at least two vectors, or two eigenvalues, one of which will be the spectral radius. Okay. Now we can use the number theory to get more information. What I'm going to prove next, I'm not going to do it today. I could. That's all right. So I can get a lower bound on the size of the eigenvalue support. And this bound generalizes, well, in a sense it does generalize one of the first results you meet in spectral graph theory. And I decided to go through it. And the lemma is you have a graph with diameter d, then d plus 1 is less than the number of distinct eigenvalues of x. Okay, so and so I'm going to give a proof of this. Someone was saying I liked algebra before. The adjacency algebra of a graph is the set of all real polynomials in the adjacency matrix. There's a complex version too, but we don't need that now. So it's a ring of polynomials in A. Now it's an algebra because it's a vector space over the reals. Not that matters too much. So when I say algebra, I'm thinking of vector space over the reals, vector space that contains the identity and has a natural multiplication. The spectral idempotents of A form an orthogonal basis for this algebra. I mean, they form a basis, and I'm just remarking that they're orthogonal with respect to the matrix, inner product on matrices. Okay, and so therefore, okay, so if you have a basis for the algebra, then you know its dimension. It's just the size of the basis. Okay, and so the dimension of the adjacency algebra is the number of distinct eigenvalues. Okay, so that gives us the right-hand side of the bound. To get to the left-hand side, the trick to notice is that if d is the diameter of x, then these powers of a plus I are linearly independent. Now, putting the I as a trick in this, which makes things actually a little easier. So what happens is you can argue that, well, a plus I to the 0 is just the identity. A plus I is the identity plus the matrix A, which we're going to assume is not the 0 matrix. And so it will have some non-identity elements off the diagonal. And so this has more non-zero entries than this does. And then I argue its totals all the way down, that at each stage here, the number of non-zero entries in the matrix increases. Now, if you leave off the plus I and your graph is bipartite, you'll run into trouble. So this is just a technical trick which makes things easier. But so the argument is that the size of the number of ones in the matrix is increasing at each step. And that then implies that those matrices are linearly independent, because you can't write the last matrix as a sum of the earlier ones, because the earlier ones are going to be 0 in the wrong place. So we have this bound. So we have a number of distinct, and so we get that this relation between the tan plus 1 and the number of distinct eigenvalues. And so, for example, a graph with if a graph has one distinct eigenvalue, then it's an adjacency matrix for identity. Okay, we didn't want that. If it has two distinct eigenvalues, this tells you the diameter is 1. And so you're looking at a disjoint unit of copies of a complete graph at the same size. Okay, so it's there's information there. Now, time. Yeah, I'll stop there. So the next step is I'm going to produce a version of this that holds using the eigenvalue support in place of the set of eigenvalues of the matrix. Okay. And that will play a key role in the proof, eventually play a key role in the proof that there's only finite emitter graphs, maximum finality K, connected, and they're admitting perfect state transfer. But I don't think I need there's not much to it, but I think I'll be kind to stop now.